All right, guys, welcome to another episode of CUDA Education. I want to make this video short, but we do have a lot of stuff to cover, so let us just get right into it, and I ask for your guys' attention. All right, first of all, we have our application, which we know very well by now, and basically it is, I gotta put things back to the way they were. Just give me 1 second, guys. 1 second. Okay, so let us get back to where we were. Okay, right. So we're very familiar with our friend here, and basically we have an application where things that are close to the camera, high level of detail. As we get down, lower level of detail, but that's only when I unfreeze the frustrum, right? So we maintain the high level of detail for things that are close to the camera. As you get further away from the camera, things in the background are less level of detail, okay? Because, you know, it's further away from the camera. Okay, so, and we could freeze the frustrum. So we discard everything that's outside of our line of sight. So we could see that when we freeze, we basically throw away everything else, okay? So that is that. Now let us get to, right, so I wanted to, you know, on the compute shader, we have our frustrum check that says, is it within line of sight? Yes, show the image, otherwise don't. Let us flip the script. So if it's in line of sight, we are not showing the image. But if it's outside of the line of sight, we are showing the object, okay? So let us flip that script. Have to compile the shader when we run it. Naturally, we discard everything outside of the line of sight, and then everything that, we discard everything that's inside the line of sight, and everything that's outside of the line of sight, we show the actual objects, right? So no matter where I rotate the camera, I still don't see objects. But if I freeze the frustrum, now I get to see stuff that is outside the line of sight, right? Because we flip the script. And naturally, if I unfreeze, things are going to disappear again, right? But if I refreeze, then we have a whole new, so you're literally looking at your monitor, guys. You're looking at your monitor. This is what your monitor really looks like. Don't listen to what Best Buy tells you, okay? Don't listen to what Best Buy tells you. This is the real size of your monitor. Anyway, all right, guys. And if we unfreeze again, we get that. All right, cool little thing. Just wanted to run that by you guys. So you can play around with it if you want. I got to make sure I'm back to baseline. Let's make sure we're back to baseline. Yes, we are back to baseline, right? And if I freeze, we get everything else discarded. All right, we're good with that. All right. As a precursor to diving into the code, we have to talk about level of detail, right? And specifically this firstIndex and indexCount stuff. But before we get to that, we have to have a discussion about indices and vertices, okay? So open with. Okay, so we have a little notes here. So if we wanted to create a triangle, let's say just this triangle right here, we have vertices 0, 0, 0, 1, and 1, 0, right? So we have 1, 2, 3, 4, 5, 6 digits, right? But if we use indices, right, and we label each indice a number, 1, 2, and 3, instead of having 6 digits, we only have 3 digits. So that's a 50% savings, right? So we only have to worry about 3 digits instead of 6, right? If we go bigger and we make a square, which includes 2 triangles, we have 1, 2, 3, 4, 5, 6, 7, 8. But there's more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? And the reason why we have all these digits is because we have to repeat vertices. So we're repeating 0, 1, right? We're repeating 0, 1, and we're repeating 1, 0, right? So because of that, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 digits that we have to remember. If we do indices wise though, we label each one 1, 2, 3, 4, we only have 6 digits, right? So it's a 50% savings right there. It's a 50% savings right there, or what have you. So the computer graphics, the computer graphics world and everything, they prefer. Oh, why is it? They prefer indices, right? So the LOD is a series of indices, okay? It's a series of indices, and each set of indices, set of 3, make up a triangle, right? Not only is the number of indices, right? So how many indices we have, but the ordering of the indices, okay? So because you're connecting up these wires, right? You're connecting up these wires. Notice that for the higher level of detail stuff, you are dealing with more indices, right? So you're dealing with all of these indices here. Level 0 is the highest level. Level 2 is the lowest level. You're only dealing with 3 indices, right? And of course, when I freeze the frustrum and I go down, these things aren't as detailed. This is detailed. This is not detailed. This is detailed, not detailed. Okay. So, more indices for each one, for the higher level stuff, less indices for the lower level stuff. We also, that's what the index count, where is it? That's what the index count is for, right? So index count is number of indices, okay? And then for the first index, you have to know where you're starting the different LODs, right? So this is a very important discussion that we have to have, right? Every mesh, every level of detail is a completely different mesh. It's not like a higher level of detail is a prefix or is a combination of all the lower level details. No, it's a completely different set of meshes, a different set of indices, a different packet, if you will, right? Because I was like, oh, why don't we just start with index 0, right? And then for the higher level indices, we just pack more. For the higher levels of detail, we just pack more indices into it. It doesn't work that way. The LOD is a long list of digits, a long list of indices, but then you have to organize it so you're starting each level of detail at a specific place, and the number of indices is, you tell it the number of indices that you need. So where do you start? First index is where do you start? Index count is the number of indices that you want. Obviously, the higher level indices is more indices. The lower level indices is less indices. As it relates to the data savings data, remember, this is a simple example, but we're dealing with 30,000 vertices, 40,000 vertices, 50,000 vertices, 10,000 vertices, 5,000 vertices, or 5,000 triangles, or however you want to slice it. The amount of data that you're shuffling around gets larger. You also have to consider that we're just dealing with X and Y. If we had a Z coordinate, all of a sudden these vertices explode in the number of digits that you have to remember, because you're gonna have 1, 2, 3, 4, 5, 6, 7, 8, 9, right? For this one, you're gonna have 3, 6, 9, 12, 15, 18 for this one, right? As opposed to just 6 here for this one and just 3 here for this one, right? So things explode and get complicated real fast if you use vertices instead of indices. So that's what the vertex buffer versus the index buffer is about, right? And I didn't make that intellectual jump. I didn't understand, what the hell they're talking about, this index buffer for the LOD, for the level of detail. And I'm like, what are you guys talking about? But now I understand. I do want to demonstrate this for you real quickly in the another example. So we're going to go to the tessellation example and we're going to run it. Okay, so when we run it, we're dealing with the wireframe. Notice that as we go down, it's less triangles and the triangles are bigger, less level of detail. As we go up, we get more triangles, more levels of detail. But notice that this level of detail, it's not just a layering on top of what we saw before. It's a completely different mesh. It's a completely different mesh. It's not the same mesh. And when we go even higher, it's a completely different mesh. So it's not like I could just combine the lower levels of details in order to get my higher levels of detail. One is not the prefix of the other. And if we go all the way deep, we get a deer, right? And yeah, we get a deer, okay? But we're not, so one mesh is completely different from the other. So it's not like you could just, pack in, more indices and get sort of, different levels of detail. No, one has to be different from the other, and also the ordering of what connects to the other is important, okay? And that is basically it. I did want to, as a demonstration, play around with messing around with the first index. So if we hard code the first index, I gotta get back to if we mess around with first index, notice that for level of detail 0, which is, the highest level, everything displays okay. But as we go to the, I have to freeze the Frustrum. But as we go to the other levels of details, notice that things get weird. And I give you guys homework to figure out why this behavior is happening, okay? Again, I'll give you the notes. We're starting LOD, at 0, right? And this is the behavior we get, right? Obviously, for the lower levels of detail, the indices count is lower. So I don't know, right? That's homework for you guys. If we start to go on the other extreme. So we start with first index of 5, which would be, you know, like down here. I have to compile the shader. We have to see what actually happens, right? So we get this guy, and oh, I gotta freeze. Which again, I'm not going to I'm not going to dive into exactly what's going on here, but you know, if we do 3, which is like middle of the road, right? If we do 3, which is middle of the road, we get this behavior, right? And I notice that for one of the levels that things display correctly, but then things get weird again, right? But I'm not going to intellectually go through why this might be the case, right? That's homework for you guys, right? So let us do the same now. Let's do the same now for the index count. So the index count now, guys, is how many indices that we're packing into the LOD. So we're hard coding it to 5, and I'm gonna see, make sure what we get. So we get this, guys. Freezer Frustrum. We get some weird stuff like a horror movie, you know, but it's okay. It's okay. We get this stuff for whatever it's worth. If we go down to 0 for the index count, we get this stuff. Notice that for this one, it actually displays correctly, but then things get weird. Okay. Again, we're tinkering with the number of indices now, right? So we're in the middle of the road, right? And things get weird, but okay. Oh no, we're not at the middle of the road. We're at, like, you know, highest thing. So let's do 3, okay? And then freeze a frustrum, and we get this. All right, so again, notice that for one of them at least, things look normal, but then things get weird again, okay? But that's a homework for you guys. You guys got to figure out what's going on with all of this stuff. Let's make sure we're back at baseline, and then we are good to go. All right, so we're at this, and we get back what we normally expect, okay? So guys, if you want to participate in all this stuff, get tutorial number 1 and tutorial number 13. Tutorial number 1 is installing the Vulkan SDK. Tutorial number 13 is installing all of these examples. I assume a Windows-based machine with a Vulkan-capable GPU. If you want to be able to run the ray tracing examples, you need to make sure your GPU is also ray tracing capable. For NVIDIA, that's RTX and above. I don't know about AMD and Intel. This example is not ray tracing. So if you just have a Vulkan-capable GPU, you should be able to run this example because it's not a ray tracing. It's not using the ray tracing features. Anyway, guys, that is it for this video. Thank you for watching. Have a great day. This is CUDA Education. Like, subscribe, tell your friends to get started on your journey. Tutorial number 1 and tutorial number 13. Goodbye.